So next up, we're going to have a panel. We have Howard Kidorf from Pioneer Consulting, who is a former Bell Labs guy who's followed subsea fiber cabling systems for a long time. We have Daryl Shares, did I get that right? Yes. From Xtera as well. And I thought this was a pretty good topic for a panel, given that we're sitting on top of the Arcos cabling system here in the Dominican Republic, which I believe has 21 spans, of which 2 have repeaters and 19 are unrepeatered. So it kind of brought to my attention a pretty cool niche within the subsea market, which is these unrepeatered systems that Daryl is going to get into. So pretty timely update. Also, with all the capacity upgrades we've seen over the last few years, and also with kind of the current state of the economy, it's kind of interesting to get these guys' perspective on how that may impact future capacity we all need. Go ahead, Howard. Oh, sorry. One last thing, I just wanted to remind everyone, do the online survey, the NANOG survey online, as well as in the front there's an operator survey in paper that you can find at the tables as you walk in the front. So please don't forget that during the lunch break. Thanks.
Thank you, Lane. Thanks for the introduction and the invitation to speak here today. I guess the first question I'd like to try to answer is why am I here and why you should listen to me. I'm a guy from a small consulting firm that focuses on submarine systems. We don't operate any networks, and in fact, I understand less than half of what you guys are talking about. So why should you listen to me? Well, I guess the obvious reason is, we make the facilities that make the web worldwide, and without a World Wide Web, a lot of us wouldn't have jobs, me included. Certainly, the failures in our field have a big impact on you guys. I've heard it in a number of talks when the Middle East has massive cable cuts, or Taiwan suffers an undersea earthquake that cuts off a big part of the world. That has an impact not just on your end users, but your businesses as well. So the way we build our cables, the way we concentrate our traffic, the way we engineer things does have a large impact on what you guys see. Certainly also our successes are important, not just our failures. Our successes in bringing down the cost per bit transported between some of the major markets also makes the services that you guys offer much more appealing. So we have a situation today where, for example, we have cost for capacity from New York to London, which is cheaper than it costs to go from New York to Los Angeles. So facilities sitting on the bottom of the ocean are costing less than just stuff that sits on the face of the earth. I guess the other reason why I think you should listen to what Daryl and I have to say is because it's a fun business. I may not be able to communicate that wonderfully, but there aren't too many businesses that we work in the internet and in telecommunications where undersea volcanoes and earthquakes matter, where hydrocarbon seeps through at the bottom of the ocean matter, where we have really neat toys like remotely operated vehicles and robots at the bottom of the ocean that help us do our jobs. Plus, we have these really big ships that can support 10 kilometers of cable hanging off the back in repair and installations. Now, when I think of submarine systems, I think of lots and lots and lots of different things. I just started typing to make up this view graph, and there's a whole list of technical things which I could spend a day talking about. Daryl could spend a week talking about all the details of fiber optics and optical amplifiers, all the things that go into making any ultra-long haul system work, like error correcting codes, all kinds of really neat tidbits about the marine environment, the animals, the physics, and so forth. Not to mention how the networks are architected. Fortunately, we have Daryl Shares here today to talk about most of this as much time as we have, but to talk about the technologies. And I won't have an opportunity to do so. One thing I would like to bring up is that we're trying to squeeze lots and lots and lots of information into a very short amount of time. So please ask questions at the end, but when we run out of time, Daryl and I are available after our talk and available through email and the phone to answer any questions that you may have. So aside from the technical stuff, there's the whole issue of the marketplace. What does the market look like? And I will talk about that first. After Darryl gives you the interesting technical tidbits, I'll also talk about what the undersea world looks like from a commercial point of view, as if you're a carrier, as many of you are, or represent or work with. What's it like to go through the timeline of putting in a cable system. So I guess no market-oriented talk is complete without talking about some of the market drivers. I'm not going to bore you with all the details because you guys aren't market people. But certainly usage growth is a big thing that you guys help drive, that we help drive. We in the world who study the marketplace care an awful lot about how fast the internet is growing, and most particularly about where it's growing fastest in what regions of the world. So we don't just look at the internet, but we care an awful lot about how Africa is doing, how South America is doing, how the east coast of Africa versus the west coast of Africa, how the transatlantic market is doing. Awful lot of study going on there. Since it's on the slide, emerging markets are very interesting to us because markets that are emerging tend to have needs for new cables going to places where they haven't gone before. I mentioned Africa in part because my company does a lot of work in Africa, but that's an excellent example of a market that's emerging. Some countries in Africa are getting undersea cables for the very first time. In fact, the whole east coast of Africa is now being connected to the World Wide Web by undersea cables for the first time. The west coast of Africa's capacity is being greatly enhanced by a whole list of new cables that are being developed. I guess I should have said it right off the bat, but we don't think an awful lot of the satellite industry as far as their ability to provide a high-band, wideband connectivity, although there are a lot of places in the world, Africa, that still depend on satellite connectivity for their internet connectivity. Market drivers, another large market driver that I've heard discussed here that is certainly that people pay a lot of attention to is diversity and route diversity. The fact that a lot of cables going to Asia from North America went through the same part south of Taiwan that was taken out by an undersea earthquake is a big problem. And still is a big problem. The fact that there's a large concentration of cables going through Egypt to get from the Med through to Asia, I consider to be a big problem that requires people to address. But some amount of engineering and investment are being placed into developing diverse routes. It isn't, 10 years ago there was a view that just simply having an SDH ring was enough to give you diverse routes. Now I'll talk about this a little bit more later, but the idea of developing submarine cables and SDH rings is almost passé. Everybody looks for multiple connections across a body of water. Some companies have policies that say minimum of our target rather is to have 5 routes, and we'll mesh everything together. It's helping to drive demand and the way things are being designed. Since I'm talking about the marketplace, I do have to address the impact of the global financial crisis. We certainly, us like everybody else who's in the infrastructure business, are holding our breaths, waiting to see how things will work out. We haven't seen an awful lot of downturn in the marketplace due to the financial crisis. Some notable exceptions, as Lane pointed out, is what used to be a lot of interest in developing cables to Iceland, for example, for data centers, is not showing up very strongly anymore. I'm personally aware of a number of banks that have withdrawn their funding, but the system developers in many of those instances have been able to secure other funding, whether it's customers who are stepping up to the plate earlier, committing more money earlier, but we haven't seen a tremendous downturn that we can attribute to the global financial crisis. On the other hand, we're not sure we would see it quite yet. The time frame for a cable system development is a year, 2, 3 years. So the things that happened last October, November, December, and that are unfolding today, we probably won't see for another 6 to 12 months. Certainly availability of capital is a huge issue for the development of new cable systems. These are very capital-intensive projects, not unlike power systems and so forth. Yet, The long-term outlook, we still think is strong. Demand is still growing double digits, 20, 30, 40% in major markets, even more in minor markets. So things look good. We're just not sure when it'll get built. The submarine system business has always been cyclical, though. So it's very important for the suppliers and the investors in undersea systems to take a long-term view. If we look back over the last 20, 30 years since people have been developing telephonic undersea cables, there have always been about cycles of about 6 years, where we go from boom to bust to boom to bust. Not huge cycles, not quite like the dot-com boom and bust we saw in 2000, but we're used to seeing cycles. The dot-com boom and bust saw an unprecedented investment in undersea cable systems, where the boom was more than 5 times the mean investment annually. The mean investment annually historically is in the neighborhood of $2.1 billion per year invested in undersea cable systems. Looking forward, we see about the same kind of investment, $2-ish billion a year in new undersea cable systems, and we are predicting quite a big slump. Now, I should point out that this slide that you're looking at is investment in new cables, not all the investment in undersea cable systems. For example, now that nearly all undersea cable systems out there are DWDM systems, the ability to upgrade them is very important, financially, certainly. And this slump that we see here in the 2011, 12, 13 timeframe will have a lot of, I'll call it infill. People will be upgrading their systems, which don't show up here. But even before the economic crisis came last December, we were predicting a downturn in in undersea cable investment. And this primarily is due to the natural cycles of overinvestment and then a withdrawal of investment. Just like we saw a huge investment in, say, transatlantic systems in the 2000 timeframe, followed by, I guess, 6 years now of no investment in new cable systems across the Atlantic. Right now we're seeing huge investment in trans-Pacific cables. Well, when that's over, that just leaves the smaller regional infill systems. Now, I'm not going to scoff at a $100 million Caribbean system or South American system or African system, but it takes a lot of those systems to make up the $2 billion per year of investment. Okay, I've got a lot of information. I'm being told move faster. I'm trying to speak as fast as I can and keep you with me. There are market opportunities in all regions. Each region of the world is independent and needs to be focused on separately. We believe that the Asia Pacific will have the largest investment in the next half a decade, in part because of the large population. The large build-out of terrestrial networks will drive strong demand in undersea cable systems, and not to mention the existing low penetration. Places like Australia, strong demand. If you look at the number of bits that every household, every person uses in Australia, it's large, but the country only has 14 million people. And so on. We can go through each of the markets. Some are more interesting than others, but they all have possibilities in the next 5 years that need to be paid attention to. The strategies for developing new undersea systems, certainly people are speaking a different language than they were in 2000. In 2000, it was a build it and they will come. Well, people built a lot of systems across the Atlantic Ocean. People did come, and it's been wonderful to get cheap connectivity to Europe from North America, but there was also a lot of bankruptcy, which again, well, not again, bankruptcy is another great opportunity for some players. Let's see. I talked a little bit about mesh networking, but the idea of deploying redundant rings has nearly died. It used to be that in the Atlantic Ocean, cables were always developed in pairs, TAT 12, 13, 2 cables for TAT 14, TPC5, 2 cables, Tata's cable across the Pacific, 2 cables. That doesn't seem to be necessary anymore. People want not only geographic redundancy, but they want commercial redundancy as well, commercial resilience. Manufacturers restricting supply isn't some kind of shady kind of business. This refers to, I guess, a strategy that the undersea system suppliers, who are very few, I can count there are 2 dominant and there's 3 other or so smaller players. The fact that they haven't greatly expanded their manufacturing capability to meet demand. They did that in 2000. They all took a bath. Some of them went bankrupt because they overexpanded their manufacturing facilities. Now they're saying, well, that's great that the world needs more cables. We're not going to build more facilities. You're just going to have to wait. The waiting list for cables, at least 2 years ago, made some people wait more than a year, sometimes as much as 2 years, in order to get their cable system, to get a manufacturing slot for their cable system. Bandwidth pricing, again, like the demand for undersea cable systems, is regional. One of the most interesting markets is the transatlantic marketplace, where we saw a huge decline in capacity pricing in the dot-com boom bust, where people now are selling capacity at very close to their incremental upgrade cost. So the cost of a transponder and undersea system gets passed on with a small markup for capacity that you guys can buy. That's not true in most other markets, and it's certainly also not something that can go on indefinitely because of the need to recoup the CapEx cost of deploying the cable initially. Every market has its own dynamic. The equipment suppliers, I mentioned that there were very few. The 2 dominant suppliers are Alcatel-Lucent and Taiko Submarine Systems, which bought the assets of AT&T Submarine Systems. Japan has Fujitsu and AC, and China has Huawei, the last 3 being smaller players than the first 2. They're doing a very effective job at managing their supply into the marketplace, but that has the effect of limiting the amount of cable that's being deployed today. The waiting list right now extends into 2011 to get a cable into a factory. Availability of cable ships also is becoming a big issue. The undersea cable marketplace competes with the oil and gas market in some ways for marine resources. A lot of people sold off their cable ships. The boom in the oil industry over the past year has taken a lot of ships off the market. So the availability, which can be translated into cost of ships, also has a great impact in the cost and speed of developing undersea systems. Something to keep in mind also, we talk about the decline in capacity pricing. It's been tremendous in the Atlantic. It's been, if you look at it globally, the cost per bit transited on an undersea cable system has been declining exponentially, just like it has on land. But nevertheless, the cost per kilometer of deploying a new cable system has been relatively constant over the past decade or 2. That's because the cost of the cables themselves is related to the cost of steel and polyethylene and copper, cost of diesel fuel to run ships and so forth. So the initial CapEx cost, if you're looking at a cable system that only is deploying one wavelength, for example, you don't see any decline in cost per bit transited because all your money is going into steel and copper. If you're looking at a fully loaded system in the transatlantic market, for example, then you see these wonderful declines. And that's due to the constantly increasing capacity of these undersea systems. I guess I could go through trying to save some time here, because Darryl and I both have a lot to say, and I'm limited at how fast I can talk. But the market is doing wonderfully today. It's booked for the next 3 or 4 years. We'll probably see a big dip in the investment in cable systems in 2011 and 2012. But the demand is going to keep chugging along, and things will return. Everyone interested in the undersea business is used to this kind of cyclical model. The investors in the business, if they've been around long enough, are used to it, but some people get burned over and over and over again. With that, I'd like to turn it over to Darryl Chairs to talk about some of the technical things, and I'll be back up to talk about what the world looks like if you're trying to develop an undersea cable system.
Thank you, Howard. Let me find my presentation here. All right, so what's interesting is, as Howard said, most people understand globalization. My friends and family, as I talk to them, they really understand globalization, but they actually take the communication portion of that for granted. So when we talk about how do we communicate with other continents, how do we transfer internet material across that, most of them have absolutely no idea. So they're fascinated when we begin to talk about this ideal of subsea cables. As Lane said, I want to focus on unrepeated subsea cables. And we're in a region where unrepeated subsea cables, because of the distances between the islands, really kind of make sense. And this is an area where internet and the communications is really building up. So I've been coming to this area, I've been going out to Asia for a number of years, and I'm really impressed with the improvement in terms of internet connection, in terms of reliability of communications. So what I want to do is just touch on the status of unrepeated technology to at least give us enough information that when you begin to ask questions, we can then delve into whatever makes more sense to you guys or what you want to hear more about. So I'm going to talk about some of the advances in unrepeated submarine technologies that allow us to go longer distances and allow us to do upgrades. And some of those upgrades really become key during times like this when people are really trying to hold on to their money. So for new systems, you get some improvement or lower cost by putting in an unrepeated system over a repeated system, but certainly you get great improvement or great savings if you can upgrade what's already there. And with today's technology, you can upgrade an old system to give you the capacity of a new system at a fraction of the cost. So then I'll go through just a couple of applications. One that shows how you extend the life of an existing system, how you take a system that has reached its initial design capacity and now provide enough capacity so that you don't have to put in a new system. So certainly when you're talking about unrepeated systems, DWDM systems, when you're looking for improvement, there's two basic things that you're looking for. Longer reach. So if you're trying to connect up to an island and the islands are 400 kilometers apart, but an unrepeated system only goes 350, then you fall a little bit short. You then have to decide if you put in a repeated system or if you have to forego actually making that type of interconnection. So I'm going to talk about some of the technologies that allow these to go longer, as well as higher capacities. As you're moving from just voice communications to data communications to video, and you're trying to interact with the rest of the world, higher capacity really makes a difference. So of course, in a submarine cable system, what technologies are involved? The very first technology, the main part of that system, is the fiber. So we have moved along and have lower loss fiber out from, back in the days when you had multiple dB per kilometer loss of fiber to today where you can have an ultra loss fiber that provides 0.165 dB per kilometer worth of loss. And certainly for a submarine system and an unrepeated submarine system, the lower the loss, the better. Advanced error correction is another technique. Advanced modulation formats, higher line rate. In terrestrial systems, we've been running at 10 gigabit, multiple 10 gigabit line rates for a while. We now hear people talking about 40 gigabits per second and going to 100 gigabits per second. So that higher line rate is moving up. Submarine systems typically trail to terrestrial systems by a bit, but unrepeated systems model more of a terrestrial system than a repeated system does. So you can actually do that, and there is an unrepeated system that has 40 gigabits per second running on it. Tighter channel spacing, and then novel amplification design. So that's one of the areas I'm really going to focus on today is the amplifier and what benefits it actually brings to both of these, the longer reach, higher capacity. Some of the technologies in terms of advances actually start out on a repeater system first and then migrate its way when it becomes more cost effective to an unrepeated system. But there's other designs that start specifically as an unrepeated system, again, as I said, to try to keep it simple, to make the system work more like a terrestrial system. So if I want to look just very quickly at an amplifier, most people that are in the transmission business understand EDFA amplifiers. And that's an amplifier that uses, as you would expect, erbium-doped fiber, where this fiber has been specifically doped so that if you pump a laser into it, you can create this energy that provides this gain. So that erbium dope part of that amplifier specifically helps create that gain. That's known as a discrete amplifier. Now today I'm going to talk to you about a technology known as Raman amplification. And the benefit of Raman amplification is that it occurs in any fiber type, so you're not limited to erbium doped fiber. The benefit of that is that you can take and really customize your amplifier based on the fiber that you're going to use out in your network, in your unrepeatered network. If it's a terrestrial network, your terrestrial network. But there's 6 or 7 different types of fibers with their own characteristics. So by being able to use any type of fiber within that amplifier, you really increase the flexibility of what you can do there. Then also you have more flexibility in terms of those pump wavelengths. So you can select the wavelength or the pump wavelength specifically to maximize your gain through that fiber. So this is a Raman version of an EDFA amplifier. So when submarine systems were first put in, if you put in an unrepeated submarine system, initially you were limited to about 100 kilometers without any amplification. You could get 300 kilometers of amplification by putting your amplifiers just on the ends. So what you're doing is saving, trying not to put an amplifier subsea, not trying to put what has been an expensive device in the ocean. Okay. So this allowed you to extend from 100 kilometers to about 300 kilometers. In addition to that, you went from maybe one channel, if it was a single channel system at 300 kilometers, to being able to do at most 32 by 10 gigabit over 300 kilometers, which wasn't bad for a while. If you wanted to increase your distance, then you could implement a technology known as a ROPA, a remote optically pumped amplifier. This is a passive device. So the benefit of this device is that it is passive, unlike a repeater in the ocean where you would actually need to still provide the power from your terminal ends to power those repeaters. A ROPA, you don't have to do that. So that is one of the benefits of an unrepeated system. In an unrepeated system, what I'm trying to do is eliminate the active devices out in the ocean, and it really saves me at the terminal ends in terms of having the power that I would need to run those stations. So if I'm putting in a new system and it's a fairly short 360 kilometer system, my savings in terms of going from repeater to unrepeated, equipment-wise, may only be 10 to 20%. But when you take into account the fact that you don't need the power to run those amplifiers, and in some of the island locations, they may not even be able to get that reliable power out there, it's a big savings. In addition, I'll show you an application where you can eliminate entire buildings, right, by being able to extend the distance and go up to, I'm going to speak of distances up to about 500, 520 kilometers. You can eliminate landing stations, so you're eliminating whole buildings and the cost of those structures, so your savings goes up even from there. So what a ROPA allows you to do is that you're going to pump from your terminal station into the fiber, again, using the pump wavelength and the fiber in that ROPA to create your gain. So it's a passive way of creating that gain. You see here that the benefits of that will give you about 60 additional kilometers, right? So we've now gone from 300 kilometers to 360 kilometers. Now, if I were to implement the same concept that I used with Raman amplification, this idea of using the fiber to create my gain, if I were to take that fiber outside of the amplifier, I've got fiber already between the two stations. The fiber is already there. If I could use that fiber to create some additional gain, it gives me additional distance and some additional flexibility. So by going to distributed Raman amplification, I'm going to distribute that gain throughout the line fiber between the two sites. I'm going to even increase the distance that I can go and increase my capacity. Okay, so by going to a distributed Raman amplification, I'm going to improve my noise figure. I'm going to reduce my nonlinear penalty, resulting in the longer amplifier span support of higher line rates. So as I'm looking to go from 10 gigabits per second to 40 gigabits per second, this is going to help out there. And also operation in the non-zero dispersion wavelength. All right, so I'm just going to quickly show, I showed Europa in the previous slide as being able to get you 360 kilometers. You could also do that with distributed Raman amplification. So again, going directly into that fiber from the receive end. When I'm making a choice of doing that, I'm making that choice sometimes based on the fiber that I have available to me, or also it could be the bandwidth that I need to use. Okay. To maximize both my distance, my length, as well as my capacity, if I stick to all-Raman amplification, I'm going to get the largest benefit. Right? So if I use Raman amplification in my discrete amplifiers, as well as in the line, as well as in my receive amplifier, I'm going to get my greatest benefit. And the way that I'm going to show this is here. Let's say on my transmit end, if I'm using a normal amplifier, I'm limited in terms of how much power I could pump into that amplifier. If I pump too much power in, I'm going to burn that fiber, right? So, it might be kind of interesting to you. You can see the 4th of July going on, but operationally it's not something you want to do. So there is a limit to how much power you can put into that amplifier, into that fiber. In addition, your signals will begin to run together. Now, what Raman amplification does, if I apply distributed amplification at the transmit end, meaning I'm going to use that line fiber, I can actually lower my transmit power, and that's what you see by this pink line. I'm going to lower my transmit power and actually use that fiber between stations to build up my gain, and so I'm not at my maximum gain until I'm 40 or 50 kilometers out into the ocean already. Then that signal begins to attenuate based on the loss of that fiber, begins to attenuate. At the opposite end, I'm going to do the same thing. When the signal begins to get so low that it's difficult to recognize, I'm going to pump from that end, build that signal back up, and then receive it at the opposite end. So from both ends, I'm increasing that distance out in the fiber, and I get myself about 450 kilometers of distance there. All right, so we talked about Raman amplification and what it has done for you in terms of increasing your distance. One of the limitations of erbium doped fiber amplifiers is that you can only get this gain over a relatively small spectrum. When I say relatively, compared to all Raman amplification, so a third of the distance. So by increasing my spectral width to 100 nanometers, I can basically get 3 times the amount of capacity. Okay. I'm going to go ahead and just kind of skip over that fiber for a little bit. So I talked about getting up to 450 kilometers. Where we are with the technology today is that if you combine these technologies, the Europa technology, the all-Raman technology, you put them together, you can now get up to about 520 kilometers worth of distance. So this is almost double what people were getting just a few years ago. It's allowing us to interconnect islands like we have in this area, take those islands and bring them back to these large repeatered systems and then connect out to the rest of the world. You see a lot of this intra-regional field going on not only here in the CALA region, but also in the Asia region as well. So in the Asia region, in the CALA region, people want to begin this infill. There is a sense of community here. They want to generate more of their own content. They want to share that, and then they again want to share that with the rest of the world. As I said, advanced error correction is another technology that's used. So the amplifiers take care of it on the amplification end. Forward error correction, as well as advanced modulation schemes, allow you to get even more incremental advancements. So one of the things that happens, I'm just going to touch on this advanced modulation scheme here for a second. One of the ones that's used today is differential phase shift keying. So what happens is, instead of modulating the light, turning the light on and off, you're going to modulate by adjusting the phase of the signal. You will basically take the signal and shift it and combine that signal back together so that when you shift the signal, if you're combining now two ones, you come together with a 1. If you're combining a 1 that has been phase shifted so that they're now out of phase, they cancel out and provide you with a 0. What this allows you to do is keep that light on all the time, right? And so you're modulating by phase as opposed to by the light. And that gives you about a 3 dB worth of improvement. If you take that 3 dB worth of improvement, if you're at the same distance, 3 dB basically allows you to double the number of channels that you can get. If you're looking for distance, you take that 3 dB and you divide by whatever the loss of that fiber is. So if it's 0.2 dB per kilometer, then you basically get about 60 kilometers worth of additional distance. Okay. As I said, higher transmission rates people are beginning to look at. So we did a quick experiment at 40 gigabits per second. We've shown the operators that you can get 10 channels of 40 gigabits over a distance of about 468 kilometers. Okay. So today we're basically showing that that technology is possible. It's still more cost effective to go with higher channels of 10 gigabit right now. And one of the reasons is that the optics on a router at 40 gigabits is still very, very expensive when compared to 10 gigabits. But the technology is there, and as it continues to move on, the price will continue to drop. So I just want to quickly show an application. I'm going to move through these next couple of slides fairly quickly. But as I said, you know, when you're looking at a 400 kilometer distance, you can either say I want to do that as a short repeatered system or an unrepeatered system. If I do it as an unrepeatered system, then I can eliminate these landing stations. If it were a repeater system, you typically keep that landing station there because the characteristics of that repeater line is so much different from your terrestrial that you want to have a digital back-to-back demarcation point. Okay? At an unrepeated system, you could eliminate that and go directly to your POP sites. You could use the fiber where the characteristics are the same. You can even use fiber in a terrestrial fiber, terrestrial cable. You can have up to 128 fibers. In a repeater system, you typically have from 4 to 8 fibers because you're limited by what you can take into the underwater housing that houses the amplifiers. Okay, so those additional fibers give you a way to increase your revenue, and you can decrease your return on investment. All right, so in this area, there is a big system called Arcos that maybe some of you guys are familiar with. This technology that I talked about, Raman technology, has allowed Columbus Network to recently upgrade this system. So this system was upgraded last year. As Lane said, this system consists of 2 unrepeated segments and 2 long or repeated segments. These segments were put in, and there are a couple of these segments that used the ROPAs when it was initially installed to get some additional distance, the longest link being 394 kilometers. So they did that at the time. That was the latest technology. It allowed them to get the longer distance, and at the time, though, they were doing maybe 4 by 10 gigabits per second. Now, because of the growth of the internet, because of the globalization, they needed much more capacity. So even though that ROPA was a inactive device, it did require, for most technologies, for you to either pull that ROPA out and move where it was going to be or get it out completely. With an unrepeated system, one of the benefits of it is that it allows you to kind of go in and upgrade without disrupting what's already there. So the Raman amplification, which used this wider spectral, allowed us to leave those ROPAs in place and just modify the equipment at the terminal ends to increase their capacity. So right now they're running with a max capacity of 23 by 10 gigabits per second. Okay, and then as I said, as we move forward, some of these links in the future, if they find a need for it, you'll be able to add 40 gigabits instead of the 10 gigabits per second, or even increase that capacity of the 23 by 10. All right, so I'm going to go ahead and just kind of summarize here, and just so that we have time for Howard to finish up if we're going to, or just
We're gonna do questions.
questions?
Yeah.
Okay, so we can have the questions. So what I really just wanted to show was the importance of submarine fibers for the continued globalization, the importance of unrepeatered fibers for intra-regional type of fields, and the importance of all-Raman technology in terms of allowing that to happen and in terms of allowing upgrades to happen. Thank you.
I'd like to open it up for questions at this point, just to make sure we have time. I know I get a sense there will probably be a lot of questions on this topic.
Hi, I'm Roderick Beck from Hibernia Atlantic. We're one of the transatlantic cable systems. You spoke about the virtues of unrepeatered systems, but I'm a little skeptical on the capacity issue. For example, our system across the Irish Sea, where there are both unrepeatered cables and our system, which is repeatered, we can put 80 10 gig waves on a single fiber pair. So can you really get more capacity with these big cable bunches on an unrepeatered system?
Yeah, so with the unrepeater system, you can do a couple of things. So as I said, you know, one of the things that you're going to, well, first of all, let's go ahead and stick to fiber, as you said. So with the unrepeater system, I showed you the commercially available doing 60 by 10 gigabits channels. The system can actually handle up to 120 versus the 80 that you spoke about. And part of that is, again, using the Raman amplification as opposed to EDFA, you have that the wider window to do it. But in addition to that, not only on a per fiber basis, but again, as we said, in terms of the cable that you use, you can use an unrepeated cable that has more fibers in it than you would for a repeated cable.
Okay, and the second question has to do with reliability. We use a repeatered cable system across the Irish Sea, 4 repeaters to be exact, and we always contend that our system is more reliable than an unrepeatered system because the repeaters can boost the signal if there's cable damage and keep the signal actually flowing through with an acceptable error loss. Whereas many of our competitors on their unrepeatered system, if they get some damage, they're down.
Well, that's a good question. So that's another benefit of the technology that's used, okay? So with the Raman technology, when I showed the distributed amplification, where you're using a pump to actually provide you with amplification, that pump will automatically adjust for some of that degradation. And we have done some work with your company as well. But that pump will automatically adjust to increase to overcome the attenuation that's introduced by that damage.
Anton Capella, 5/9's Data. Excellent presentation. Very interesting to see about the parts I never get to see about. One question, or actually two questions. The first one was, is there an OEO buffer, if you will? You kind of alluded to that, but I don't have any experience here, so I'm wondering, is there some sort of an OEO buffer that shields the customer from anything that they could do, good or bad, or whatnot, on the DWDM portion across the undersea?
Yes.
I'm guessing there is, but does that then mean that you have the ability to take, like the second question was, receiver thresholds and such? I know you mentioned on the technology slides there were improvements across the board, but what I'm curious about is who or what, or is anyone working on just getting a more sensitive receiver? Is that anywhere to be improved? Because again, if it can be done on your edge, between your optics piece over the long segment, what faces the customer is a buffered locally, 1310, 1550, whatever. So if you can improve that performance of the receiver, does that benefit the reach for you?
Sure. Yeah, so let me start on that, and then if you want to join in, Howard. So there is a demarcation, an OEO demarcation. So one of the slides that I showed pop sites, and I showed the substation. Mm-hmm. That substation is where the OEO would typically occur, okay? And through that, so the substation is where the OEO occurs, and it does buffer people to the outside of that from some of the degradation. Most of what I talked about actually happens in between there. In terms of receiver sensitivity then, That is worked at both levels, both at the OEO level, but then also there's additional work that's done on the optical side, right? So some of that receive level is done in terms of that preamplifier that we had.
Thank you.
Just want to add anything?
Had a two-part question. First one was for
Name?
Matt Siniscal, Mid-Atlantic Crossroads. First part was for clarification. We speak of repeaters. Are you speaking of pure all-optical amplification, either EDFA or Raman, or are you speaking of a 3 Rs regeneration OEO conversion?
It could be either one.
Okay. The second
I'd like to
part.
clarify that.
Sure.
I mean, the repeaters that are undersea today that are being deployed are all optical and are purely optical devices. Regenerative undersea repeaters haven't been deployed since the early to mid 90s. So they're all
TAC-10,
full
yeah.
WDM, erbium doped fiber amplifiers.
Okay. Second
All
part.
right, let me interject there. So this is a good thing about a panel, so you could go back and forth. The reason that I said that it could be either one is that we are actually upgrading short repeater systems, and those short repeater systems, as Howard said, you have systems that were put in the mid-90s that are OEO. We are upgrading one that has an OEO. Those systems are generally designed for 25-year lifespan. But where the technology is right now, you actually want to use today's technology to get you the capacity that you can do. So we're upgrading both the all optical type repeaters as well as the OEO repeaters.
Okay. And the second part is strictly referring to the new development of cable systems. What is the maximum distance you think theoretically in terms of bandwidth distance product on an all optical system? In terms of channel count, if you're using Raman with repeaters in the middle of the ocean, theoretical, or at least a practical theoretical, 120 by 40 gigs over 5,000 kilometers?
Yeah, so let me start with the answer, because so you asked two parts. So first of all, what I was focusing on was unrepeated, so there's not Raman amplifiers out in the ocean, okay? The slide that I showed where we showed 468 kilometers, we actually did we've actually shown that you can do 120 by 10 gigabits per second on that system. I also then talked about 520 kilometers. When you go beyond the 450, 460 range, you're going to begin to drop down. So at 500 kilometers, and we're talking about a maximum of about 4 by 10 gigabits per second.
So then adding on to that, and when you're doing a multi-repeater system, you can correct for losses ad infinitum, but the problem really then becomes aggregation of CD and PMD. So that's your ultimate limitation on your distance before you have to go for full 3R regeneration. What do you think that distance is? Go ahead.
On repeater systems, first I'd like to thank Darryl for clarifying that Raman doesn't have much of a role in repeater systems. Although it's theoretically possible to have Raman in undersea repeaters, it has never been done, nor is it likely to happen in the next bunch of years. The state of the art today for undersea long-haul repeater systems is roughly 96 wavelengths per fiber pair, and a system can handle up to 8 fiber pairs.
Max speed per minute. You're talking about 10 gig waves?
Sorry, each wavelength is 10 gigabits per wave, yes.
Yeah.
The suppliers are talking about doing 128, and that's quite reasonable also, wavelengths per fiber pair. And as far as distance goes, it's hard to find a good limitation. Systems longer than 10 or 11,000 kilometers have rarely been proposed. So there are systems with 96 wavelength capacity, 8 fiber pairs going from the west coast of the United States to China today, and that 10 or 11,000 kilometer range is easily within their sweet spot.
All right. Thank you.
We have another question over here.
Okay, Rihanna from Agni. Great presentation. I have a question about the slides that you were showing, your plot of distance. The last one was for 360 kilometers, etc. I could see in the old EDFA plots, you always finish with the sensor sensitivity of around 20 something, minus 20 something dBm, but in the other ones, the ones that you had distributed Raman, you always finish in 0. So I wonder if there's actually some more kilometers that you can go on, just leaving that to the receiver sensitivity. Or that was confusing for me.
Okay. Yeah, let's.
I don't know if you can show it. Yeah.
Yeah, if he pulls that back up, I'm actually showing both of them to be
Any
0.
of those you finish, this on the ones on the right you finish in 0, but the one on the left is, I guess this receiver sensitivity is minus 40 dBm.
Well, what's happening though is even on the 300 kilometers, when the representation of this line going up to 0 represents that preamplifier, bringing that signal back up to a 0 level.
Oh, okay. So you're saying in the other ones the preamplifier is distributed. That's why it goes smoothly. It doesn't go
Exactly.
sharply.
Correct.
Okay. And the second question I have is what's the state of the art about dispersion? Because you're always talking about like everything is attenuation driven. The distances. Your problem is attenuation and power. But there's many times that actually the problem is dispersion, and you need to compensate dispersion,
Exactly.
et cetera.
Yeah. So what happens is when we're speaking about dispersion, as the light is traveling down that fiber, dispersion causes the light pulses to increase or decrease. It basically distorts those light pulses. So I didn't spend a lot of time talking about it, but what I was trying to get across was that if you're designing a system, you're correct. Generally, in an EDFA system, you have erbium dope within the amplifier. To compensate for the dispersion, you have dispersion-shifted fiber outside. That dispersion-shifted fiber costs you additional money to put that fiber in, and it also costs you in terms of loss. It's a very high-loss fiber. But because Raman amplification can occur in any fiber type, you can actually take that dispersion-shifted fiber and you use it in the amplifier as part of the gain medium. So instead of it creating a loss, it actually creates a gain. So you end up with a gain.
But you're using the non-zero dispersion shift fiber. Is that the one?
You can use you select the fiber based on the characteristics of that line fiber that you want to match. Okay, so there were cases that I talked about dispersion shifted fiber. There are cases for non-zero dispersion shifted fiber. It's going to depend on what fiber you use, and the dispersion's managed differently.
And in order to get this 450, do you need to do something with PMD? Do you need to get some sort of
No. So the general answer is no. Okay. If we're talking about trying to upgrade an older system, and that older system was put out before PMD was really given as a specification that people had to follow, then it is possible. But generally, on the new cables or cables that's been put out since the late 90s, you don't have to worry about it. If you go to 40 gigabits per second, again, if it's an older fiber, it is something that you do need to worry about. So it's going to vary. But so far, in terms of the systems going from 2.5 to 10 gigabits per second, PMD is no issue.
Thank you.
I think we have one more question over here.
Kevin Hodel from One-to-One Internet. Generally, in a traditional repeatered system, you would also, in addition to the bundles of fiber, you would have to run power to each regeneration point along the way. Is that correct?
That's correct.
Okay. So with the repeaterless system, you no longer have to have this additional power cable along with the bundle of fiber. Is that correct?
That's correct.
Okay. And does that reduce the overall initial expenditure to build out the system?
It absolutely does.
Okay.
Yeah, that's one of the bigger pieces.
Okay.
Yeah. So what's interesting? I mean, you did hear me throw out a number of 10 to 20%. Again, just kind of comparing the equipment cost. But when you start looking at the power costs and the buildings and those type of things, that's when the savings adds up. Yes.
Good. Thank you.
Thanks, guys. I think one of the other interesting things when I was talking to the speakers earlier was some interesting tidbits like the fact that the oil boom caused a tripling of prices for access to ships to lay cable, and that's kind of settling down again now. So some interesting factors with the economic slowdown that's going to make it probably cheaper for some of these projects. We have lunch now, so thank you for your attention. We have lunch now until 2:30 p.m. local time, and don't forget to get your survey, your operator survey at the front desk on your way out, and do your surveys online. Thanks.
Thank you.